everyone. Today we are going to go over energy conservation when friction is involved. And we're going to look at that both on a horizontal plane and on an incline. And the great thing about this is when I look back at people's reflections of the last video, the one area where people said that they were still kind of confused was with the non-conservative forces, which makes sense. I knew that we were going to cover this today, so I didn't go into it in way too much detail yesterday. I just kind of wanted to give you a little bit of a feel of where we were going. So when we look at this first question, this is question number 13 on your in-class practice problems. I have a 5 kilogram box is pressed against a horizontal spring. So that horizontal spring has a spring constant of 5,000 newtons per meter, compressing it 0.4 centimeters from equilibrium, which is a distance of 0.4 meters, so 40 centimeters, 0.4 meters from equilibrium. The spring is released from rest, launching the block across a rough, flat surface. So we have our spring, okay, and we have this compression, and then once it's compressed, it's going to be launched this way, okay? And it's the friction, coefficient of friction is equal to 0.15, okay? That's the coefficient of friction. And it's asking what is the speed of the box when it's measured meters after losing contact with the spring is 3.6 meters. Okay. So after losing contact, we have 3.6 meters. And something that would be an easy mistake here that people would make, and I understand why you would make the mistake, is really the distance that's being traveled by that block during that frictional force is equal to the 3.6 plus the 0.4. So the block is sliding against this frictional surface for a total of 4 meters. And that's important to take into consideration. So what are we looking at here? We're looking at our mechanical energy initial. Our total energy is mechanical energy initial minus the work done by our non-conservative force. And the work done by our non-conservative force is friction. And in yesterday's video, I said that in any of the equations, you're going to see plus non-conservative force. But the way I see it is it's work that's being done against the block. And so it's taking away the energy. And then that's equal to our mechanical energy final. So another thing that I talked about yesterday is splitting up the mechanical energy into what are the different types of energy. Well, if we look at gravitational potential energy, we are not dealing with gravitational potential energy. In the very beginning, we don't have kinetic energy. We only have our spring potential energy, which is 1/2 kx squared, okay? And then we take away our work done by friction. So we have our frictional force, our force of friction, okay, times the distance that our friction is working. And that's equal to our mechanical energy final. Well, again, we're not dealing with gravitational force. And at this point, we're not dealing with spring potential energy because if we were looking at spring potential energy, it would still be attached to the spring, and it's not. So we look at that as 1/2 mv squared, and that's your final velocity. Okay. Now your frictional force is going to be equal to your coefficient of friction times your normal force, remember. So we have 1/2 K, which is going to be 500 newtons per meter times our x squared. And our x is 0.4, and we're going to square that, okay? Minus our frictional force, which is 0.15, times our mass, and our mass is a 5 kilogram mass, times our gravity, which is 9.8 meters per second squared. And then multiply that by 4 meters. Okay, this is meters. This is meters per second squared. This is going to be kilograms, paying attention to our units, equals 1/2 times your mass, which is 5 kilograms, velocity squared. And when I rearrange that entire equation, I end up getting that my velocity in the end, my V final, is equal to 2.06 meters per second. 2.06 meters per second. Now, if I look at this next question, we have a boy on a sled with a combined mass of 80 kilograms is going up or going down a hill, sliding down a hill with a 34-degree angle. That is 25 meters long. If the coefficient of friction between the sled and the hill is 0.15, calculate the sled's speed when it reaches the base of the hill. So when we look at this question, okay, we have our person, okay, sledding down our hill, okay? And our hill is going to end up being 25 meters long. So he's sliding against friction with 25 meters, okay? And we know that the angle is a 34-degree angle, okay? And so let's see, what is our mechanical energy initial? Well, our mechanical energy initial is going to be dependent on, so we're looking, do we have spring potential energy? We don't have spring potential energy. Do we have kinetic energy initial? We do not have kinetic energy initial. Do we have gravitational potential energy initial? Yes, we do. Okay, so then I'm going to take away my work done by my friction in this case, and then I'm going to have that is equal to my final mechanical energy. Okay, well, what's my mechanical energy final? We're looking at the sled's speed when it reaches the base of the hill. So do we have spring potential energy? No. Do we have kinetic energy final? Yes. Do we have gravitational potential energy final? No, because we're setting our height as being equal to 0. Okay, so what is our mechanical energy initial? That's going to be mgh, but how do I figure out what h is? Well, mgh, h is going to end up being my 25 meters times sine 34, because I'm really just looking for this height right here. So mgh minus my work done by friction, which is going to be my coefficient of friction, okay? My coefficient of friction times my normal force. Okay, well, my normal force is going to be a little bit different because I'm dealing with something on an angle, and then times my distance. Okay, and that's equal to 1/2 mv final squared. So when I go ahead and plug that in, okay, I have my 80 kilogram child times my 9.8 meters per second squared times my height. And remember, my height is going to be 25 sine 34 minus my frictional force, which is, or my coefficient of friction, which is 0.15, okay, times what's my normal force? My normal force, if we remember from last unit, is going to be my gravitational force down in the y direction only. So I have 80 times 9.8 times cosine 34, okay, and then times my distance. And my distance is going to be 25 meters, okay? And that's all equal to 1/2 times the mass of the boy, which is 80 V final squared, okay? When I go ahead and plug everything in, so I'm going to multiply both sides by 2, divide by 80, and take the square root of that, I end up getting V final is going to be equal to 14.6 meters per second. So if we need to walk through this problem again, you have a child sliding down a hill, At the top of the hill, the child has a gravitational potential energy, and that's the only energy that the child has that's dealing with this system, the sled, child, and hill system. Okay. So at the very beginning, when the child is all the way up here, okay, you end up having mass times gravity times height. Okay. Now, as the child is sliding down the hill, friction is acting against that child, and friction is acting against that child the whole entire time. So friction is acting against that child at a distance of d. Okay, so acting against, that's where we have our negative sign. And then our frictional force is the coefficient of friction times normal, and it's acting for a distance d. So that's the work being done to slow the child down. Okay, now it's not going to be much because the coefficient of friction is really small. Now we want to figure out how fast is that child going at the very bottom. So that child no longer has gravitational potential energy. That child is really only going with kinetic energy at this point. The kinetic energy is 1/2 mv squared. So we're solving for our v final in the end. So you really, as you break down these questions, you really start to kind of see like what is being asked. And if you're not there yet, you're not there, and you'll get there, I promise. Okay. Now, the next thing that we're going to talk about, and the last thing that we're going to talk about when it comes to work and energy, is power. Power is the work done in a certain amount of time. So it's the rate at which work is done. Power is equal to work divided by time. So if our power is equal to work divided by time, well, we know that work is equal to force times distance divided by time. Well, that's helpful. But we also know that distance divided by time is velocity if it's constant. So if you have a constant or average force, that's your average force or your constant force, times your average or your constant velocity times your constant velocity, you can end up getting power. Now, what is power measured in? Power is measured in watts. 1 watt is the same as 1 joule divided by seconds, which is the same as newtons times meters per second. So there are some things that we need to remember. We're dealing with kilowatts a lot of the time, or kilowatt hours. And so when we're dealing with kilowatts, 1 kilowatt is the equivalent of 1,000 watts. And all of you know that, but I'm just refreshing your memory on that. And then the very last thing is just the knowledge that 1 horsepower is the equivalent of 745 watts. If you're given a question about horsepowers, knowing that 1 horsepower is equal to 745 watts is helpful. Okay. So this first question right here says, how long will it take for a 700 or 7 horsepower motor to lift a 500 kilogram crate upward by a distance of 4.2 meters? Okay, so one thing I said in the last slide is that a horsepower is 745 watts, but it's 746. So 7 horsepower, what is that in terms of watts? Well, 746 watts are in 1 horsepower. So when I do that, I end up getting 5,222 watts. 5,222 watts. And that's the equivalent of 5,222 joules per seconds. So I'm trying to figure out how much time does that take? Well, I know that work divided by time is equal to my power. So my time is equal to my work divided by my power. And my work is the equivalent of force times distance divided by power. Now, my force here, if I'm lifting a 500 kilogram crate, then I am going to put my force as 500 kilograms times 9.8 meters per second squared. My distance that I raise it is 4.2 meters. And I divide by my power, which is 5,222 joules per seconds. Okay? And so that's going to end up giving me that my time that it takes is 3.94 seconds. So most often, these types of problems with power, we want to figure out how much energy is required in a certain amount of time to lift something. How much energy is required in a certain amount of time? Okay, for if you have that power coming from your motor or that power being exerted by a person, whatever it is. Okay. So let's look at our last question for today. And our very last question for today says a small motor uses a rope to pull up a 3 kilogram block up at up a 20-degree incline at a constant speed of 5.2 meters per second. Constant speed of 5.2 meters per second. If a frictional force of 7 newtons impedes the block's motion, what power is required of the motor? Okay. So in this case, we're looking at, again, power equals work divided by time, but that's not really going to help us greatly. Okay. What we're really looking at is we're looking at the power, and the power is the force times the velocity. The force times the velocity. Okay. So what we need to do is we need to figure out what the force of the motor is. So if I have my incline and it's a 20-degree incline, okay, and I have a rope pulling a 3 kilogram block up the incline at constant speed, the 7 Newton frictional force impedes that. So we have the force of the motor. This is the force of the motor. And we have, because it's a constant velocity, my sum of forces is 0, right? My sum of forces is equal to the force of the motor minus my frictional force, which is going to be 7 newtons. If you need a reminder, that's your frictional force, your force of friction, minus my force of gravity. Okay. But this is my force of gravity along that incline. Okay. So force of gravity in the x. And that force of gravity is going to be mg sine theta. So 3 times 9.8 times sine 20. So I end up getting that the force of the motor, the force that needs to be applied by the motor, is equal to 17.1 newtons. And then I'm going to go ahead and plug that in up here. So I have 17.1 newtons times the velocity. And the velocity in this case is 5.2. Okay. So if the velocity is 5.2, and that's going to be in meters per second, then that's going to end up giving me 88.9 watts. Okay. So this is a what power is needed. I mean, I could be talking about anything. What power is used in your house? What power is used by a light bulb? You use power all of the time. You use power every single day. So remember, power is work divided by time, but that can also be converted into force times your constant velocity. Hopefully that was helpful for you today. If you have any questions, make sure that you go ahead and reach out.